will be John McGreevy, who will finish off his introduction to ADS-CX.
Good morning. Thank you to you all for waking up. So today, the third lecture is going to be much more directed towards those of you who are wondering, those of you who maybe for one reason or another know about the machinery of ADS-CFT, but are wondering how in the world one could possibly use it to say something about condensed matter physics. Where's my stick? Right. And so in particular, I want to talk about Fermi surfaces. Though I guess I should say that the calculations I'll talk about will still be rather elementary, and so I don't think I'll have to lose anybody. And I'm going to start with a discussion which is actually the same classification of states of matter that Subir talked about yesterday. Organized by what are the degrees of freedom that we have to include at the very lowest energies, so at E equals 0. So the simplest possibility is a system with a complete gap, so where the energy spectrum is something like this, where there's nothing below some finite value, where the effective field theory is a topological field theory, even if it's one that we don't know about yet. It's just a theory of the ground states. The next case is the case where there are gapless excitations at points in momentum space. So a relativistic critical point, or sometimes this also happens on the surface of some insulator. In which case, the effective field theory is something which is some sort of scale invariant theory, where we scale towards the origin of momentum space, scale towards the interesting point in momentum space. And I say that this is we're doing pretty well on this case in the sense that we know what the right framework is for discussing the low energy physics. That is, we should think about the renormalization group, a renormalization group which scales towards this interesting point in momentum space, which therefore will scale towards, will include the low energy excitations. And then the third case is much less well understood, which is the case of systems which have a Fermi surface, by which I will also mean some excitations on some finite dimensional, higher than 0 dimensional locus in momentum space. And maybe for illustration of the at least my own impression of the levels of understoodness appearing in this picture, let me make a musical analogy. So this case is sort of classically understood. It's maybe even a little boring. I mean, there's some topology involved maybe, but we pretty much know what's going on. And this case is sort of maybe a little more modern, but still something your parents think about. And then this case is just totally out of control. And so it's a little subjective, but I think it's apt. So here's what I want to do today. I'll say a little bit more about what we need for an understanding of systems with Fermi surfaces. Then I'll talk about sort of a first attempt that some of us made in the direction of constructing holographic states that exhibit Fermi surfaces, where we can understand quite a bit about them. And then I'll say a little bit about why this is clearly not the end of the story. There are many reasons. I'll talk about some of them, and then I'll talk about attempts to do better than that. Some of which are quite recent. So that's the plan. And so I'm gonna let's say reaffirm some of the things Subir said yesterday about our understanding of metals. And so just to orient ourselves in the world of things that are understood, let's think about the answer to this question that we know. So a basic question is, what is the right description, the right effective low energy description of a system that has a Fermi surface? And the answer to this question that we know is, and in fact for a long time it was believed was the only answer to this question, is that it has to be a Landau Fermi liquid, which means that it's continuously connected without any dramatic events to free fermions. Let's back up even more and let me remind you about that. So remember, if the fermions were free, we would, if we had a bunch of free fermions, we'd fill the single particle states, which, since I'm I used to be a particle physicist. I think about particles living in free space, in which case their dispersion is something like this, and we fill the single particle levels until we run out of fermions. The last momentum that we reach is kF, and the energy that we reach is the Fermi energy. And the low energy excitations are achieved by adding the next a fermion in the next level, or removing one of the last ones you added. And the idea of this Landau theory is that there is an interacting theory where you turn on interactions between these particles, but where the low energy excitations are still of the same nature as these guys in the free theory. They're still weakly interacting, fermionic, charged particles. And so of this list of words, the last one is maybe the most important one. So the statement that they're particles means that there's some sort of approximate energy eigenstate that has definite momentum, which you can make a wave packet of it, and it propagates for a long time, and it decays. Before it decays, its wave function oscillates a bunch of times. So it's really a sharp resonance. And the picture you should have is that this is the free fermion. When it's hanging out with its friends, it has to drag around some cloud of disturbance of its friends, but it still is roughly has roughly the same properties as it did in the free theory. And these words I was just saying about the existence of long-lived quasiparticles has a consequence, for example, a quantitative consequence, for example, for the single fermion Green's function. So let's think about the retarded Green's function, where the two operators that are involved are the operator that creates an electron and the operator that destroys it, or maybe in the other order. It's the difference of the two orders with the theta function. And in the Landau theory, there's a surface of poles in momentum space. So this is here. This is at the set of points where k. So I'm thinking about a spherical Fermi surface because I want to live in a nice rotation invariant, translation invariant continuum for simplicity. And so this is some locus of points where the momentum vector has radius, has length kf, and where at zero frequency there's a pole. So so you see, if I ignore this imaginary part, this describes an excitation whose dispersion is linear in k perp, where k perp is the direction perpendicular to the Fermi surface, and there's a residue of this pole, which is some finite thing, and then this gamma is some small thing, which we can think of as a correction. And this in the case where I'm talking about the electron Green's function, this is something that can actually be measured. I think it's useful to emphasize that saying that the system has a Fermi surface is, at least an electron Fermi surface, is something even positivists can get behind, and it's because you can scatter light off of your sample with some known frequency and momentum, and by the photoelectric effect kick out an electron, which you then observe and whose frequency and momentum you know, and then you take the difference of those, and that's the frequency and momentum of some excitation in the system with the quantum numbers of the electron, or I guess the absence of electron, and by measuring the intensity that you see as a function of the frequency and momentum, you get a picture that looks like this. This picture was actually generated by a holographic calculation, but a picture that looks like this, where at some non-zero value of momentum, there's some spectral intensity, some intensity of the result of this experiment, which disperses through zero frequency. Linearly in the deviation from the Fermi momentum. And this intensity, this photoemission intensity, it's in some good approximation, is well described by the imaginary part of this electron Green's function. Which, if we're doing this experiment on something well described by the Fermi liquid theory, when these frequency and momenta are near the Fermi surface, this approaches a delta function, right? So this resonance becomes sharper and sharper, and right at the Fermi surface it becomes a delta function with some finite weight, which is this residue, as you can see by taking the imaginary part of that. And if the origin of the lifetime is from electron-electron scattering, then this width of the resonance goes like the deviation from zero frequency squared. Okay, and so these properties that are described, in particular, the fact that the system is well described by long-lived quasiparticles sort of the essence of what allows the theory to be calculable, what allows you to calculate things like thermodynamics and transport in a way that we can trust. And I want to say two things about why there exists this lore that this is the only possibility. It's not just lack of imagination. One is that this theory is wildly successful. It describes well like all systems with Fermi surfaces that people thought about, or that people thought about carefully until the 80s or so. And then the second is actually a calculation. There's a conceptual reason that you might think this Landau Fermi liquid theory is inevitable. Namely, if you think about this Fermi liquid fixed point, the operators that we include in this theory are the excitations of the fermions near the Fermi surface. And if you ask, how can I perturb this fixed point in such a way as to move away from it, and analyze the theory with the renormalization group, you find that, in fact, nearly all of those possible perturbations flows back to the free fermion fixed point, to the Fermi liquid fixed point. So they're all irrelevant operators, except for one important footnote, which is the BCS instability, which leads to pair condensation. Yes, good. Yeah. So all right. So that's hidden in the fixed point coming out of the board. Yeah. Yeah. Good. All right. So it's actually a family of fixed point, as Sabir is pointing out. Good. So, but nevertheless, in spite of this, these very convincing arguments, there are other things in the world, and I guess the best reason to think that there are other things in the world is experiments, which, and I guess, and so there are many interesting materials which, in parts of their phase diagrams, exhibit behavior which is deviant from this nice theory we just talked about, and one way in which some of them deviate, for example, the high temperature superconductors in this strange metal phase, is that if you do this photo emission experiment, which people have done quite a bit, you see that there is a Fermi surface. So there is a locus in the momentum space where there are gapless excitations away from zero momentum, some finite dimensional locus. So there is a Fermi surface, but if you look at the dispersion of the excitations near the Fermi surface, it's certainly not it's not well described by long-lived quasiparticles. In particular, it's a broad resonance near the Fermi surface where the lifetime is a vort of the frequency. So that is the wave function of the would-be particle. Its phase goes around once in the time it takes to decay. So it's not a very well-defined particle, and also I think it's plausible to say that the residue vanishes, though I guess you can't really tell that from these pictures. Rather, I guess you can tell it from the fits to the pictures, which I'll talk about a little bit. And so a useful working definition of a non-Fermi liquid, for the purposes of this, let's say this lecture, is a system where there's still a sharp Fermi surface, so some zeros of the inverse Green's function at k non-zero, omega equals 0, but where the excitations there are not long-lived particles. And I guess I have to say that this is a sort of delicate property that you have to do a lot of analysis to see in this very modern photo emission experiment. The most obvious way in which these things differ from Fermi liquid is just in the transport properties. You just to measure the DC conductivity, and the answer is this linear T behavior, which is very different from the answer that you get from any reasonable mechanism for dissipating current in a Fermi liquid. So this is a provocative slide. So superconductivity gets in the way of our very important study of strange metals. And some evidence that this is the right perspective is you can prevent the superconductivity from happening by putting the system in a big magnetic field. Ignore the red curve. My emphasis is on this curve, which is one of these optimally doped high temperature superconductors. So somewhere here, in a field that's big enough that what would have been Tc is somewhere, I don't know where it is, somewhere around here. And this linear T resistivity, this is temperature, persists down to the lowest temperatures that you can see. And so, this, it looks like it's pretty straight, though I guess, I don't know, my colleague Senthil, for example, spent a few months trying to convince, staring at these plots and arguing that in fact they were not straight lines, and he's probably right. But this picture is suggestive that this superconductivity is some annoying instability of this strange metal state that's getting in the way of our studying it. It also suggests that perhaps what we should be looking for is some sort of intermediate scale description, some state which is not necessarily arbitrarily stable down to arbitrarily low temperatures, much like the Fermi liquid theory is. So, yes.
Difference in physical meaning between the fact that you have zero residue and non-zero residue.
The difference in physical meaning. Yes, good. So the way you should think about the residue is it's the wave function overlap between the actual electron that you're kicking out of the system in this experiment and the quasi-particle excitation. And so the statement is that right at the Fermi surface, the excitation is something other than this electron. It's the overlap goes to zero. Exactly how to accomplish that, that's sort of the question. But it's like saying that the wave function normalization is as big as it can be. The wave function normalization is as big as it can be. Yeah, so that's one reason to call it Z. Okay, so let me say a few words about non-holographic attempts to understand non-Fermi liquids. So this is, that phrase used to be a joke. So I should say that with the definition I've given, there's a beautifully understood realization of this physics in 1+1 dimensions, which is the Luttinger liquid, which is can be realized as a deformation of free fermions in 1+1 dimensions by some four-Fermion interactions, and where the Green's functions we know for sure have this behavior in frequency and momentum, and so where this k is really k perp. In one dimension, there's just Fermi points, so that shift doesn't matter too much. And you see, this thing is certainly not. It's certainly not. The singularity at the Fermi surface is certainly not a pole. It's rather some power law kind of junk. Not junk. It's not junk. Some power law kind of stuff. And all of you, certainly those of you who do streak, I guess everybody knows about Luttinger liquids, right? Because condensed matter physicists know about it because it exists, and string theorists know about it because it's free bosons, right? It's realized on the world sheet of strings propagating on circles, so you all have to know about this. So the reason we know this is because of bosonization, right? We can bosonize these fermions, and they're just this fixed point is described by just free bosons at some radius other than the free fermion radius. So one dimensions is done. Or it's not quite done. That's not quite fair. There's more to say about one. There's an example. There's an example.
This is really more like a Fermi liquid than a non-Fermi liquid. Well, ignore that. Go on.
Okay. I take back my statement that one dimension is done. Rather, there's a really good example in one dimension. Right? It's not quite as burning a question. At least if the thing we're interested in is this Green's function. Yeah. So other properties, surely other things can happen. Okay. So I guess it's also useful to say that the Hubbard model probably includes this physics. People have made some progress towards extracting it, this information numerically. Exactly why it happens is, I think, well, there's some useful pictures, but I think it's still kind of a mystery. But I think by far the most progress towards constructing theoretical descriptions of non-Fermi liquids has been through this loophole, through an important loophole in the renormalization group argument for the inevitability of the lambda Fermi liquid, which is this argument that all of the perturbations were either irrelevant or marginal, and therefore within the Fermi liquid theory, or BCS, assumed that there were no other low energy excitations out of which we could make operators besides the fermions. Right, so that was an implicit assumption in my statement that we tried to add all the operators. And so if there's some other arbitrarily low energy degree of freedom, then something interesting might happen. And the list of possibilities for what that degree of freedom could be bosonic. And if it's a boson, the list of possibilities for how you might end up with some gapless boson is long. It can arise, for example, if at a phase transition, right, as the fluctuating order parameter for some quantum phase transition, or it could arise in a phase, where in a situation where its gaplessness is protected by some sort of emergent gauge symmetry. And so I guess Subir is going to talk quite a bit more about this diagram and its consequences. So I won't say too much, but I will say that it does lead to the kind of non-analytic behavior of the fermion self-energy. That is the thing that goes here in the Green's function, which is enough to make the residue at the Fermi surface 0 and to make the lifetime of the particle short compared to its frequency. So this is enough to, such fluctuations are enough to kill the quasi-particles. Let me make some complaints about this way of killing the quasi-particles. The first one is sort of cheap. It's, our understanding of these theories is perturbative, and the interesting effects that we're looking at for these non-analytic terms are proportional to the parameter that's controlling our perturbation theory, like 1/n. And so, in order for our perturbative answer to be parametrically reliable, that means that the effect only happens at very low frequencies, very low temperatures. This is kind of cheap. This is like an argument against perturbation theory in general, and perturbation theory is often quite good. Okay. Secondly, this control parameter that I was implicitly thinking about here, which is the number of fermion species, is not entirely successful at controlling the perturbation expansion, and this Subir is going to talk about, so I won't say anything else about it. But then I think most importantly, these are some arguments about calculations, or not arguments, but comments about the way we're studying the theory. The most important reason why this is, there's more, it's clear that there's more in the world in this construction, is that these strange metals are not strange enough, in the sense that although the Landau quasi-particles are killed by these gapless boson excitations, the way that they're killed means that the transport properties are not strange enough in the following sense. So this is the diagram by which the quasi-particle decays. The thing it decays to is another quasi fermion state. So I'm computing the imaginary part of this diagram by cutting it here. So the thing it decays to is a fermion with a slightly different momentum and this gauge boson. And thinking about, I guess I get to use Fermi's golden rule here. This amplitude for decay is proportional to the density of states of this boson that admits, and the fact that the low energy excitations of that boson are supported at the origin of momentum space means that it's most likely to emit a very low momentum boson, and that means that this state is very likely to have nearly the same momentum as this state, and therefore it carries nearly the same current. And so although it's the death of this quasi-particle in every sense you might mean, it's I guess there's not a good analogy, but it's still carrying nearly the same current, and so the electrical conductivity isn't the electrical resistivity, that is the dissipation of current, is not as efficient as as it could be given the shortness of the quasi-particle lifetimes. And so the practical consequence of this is that even in models where you get the lifetime right of this form, the behavior of for example, the DC conductivity, the DC resistivity will be it'll be smaller than it would be if you just used dimensional analysis from this formula. If you just use the same, not dimensional, if you use the same exponent here. So in particular, it won't be linear in T, in the case where this thing is of the form that we think it should have.
There's a small loophole here also.
Mm-hmm.
I have to also so small. If you mean any gapless boson, now it could be
that they're sitting at somewhere other than zero momentum.
Q of the boson is actually a big momentum on the lattice.
Yes.
What happens for the anti-ferromagnetic?
Right. Yeah, good. Well, but I guess the tricky thing there, though, is that then it only kills the quasi-particles at some points on the Fermi surface, right?
Right. That's not fully understood.
Okay. Yeah. So as you can see, this is a provocative remark.
I agree with it for most cases.
Okay. Okay. But I'm using this to try to motivate the search for other non-Fermi liquids, which I think everybody can get behind. And so in particular, I think even no matter what, I think it would be very nice to have a non-perturbative description of such a thing in more than one dimension. And so this is given the serious poverty of our understanding of how to describe systems with Fermi surfaces at the lowest energies, this is a question that we can ask holography, where even if the thing we're getting it from is secretly at short distances some relativistic superconformal gauge theory with lots of colors, if it produces some non-Fermi liquid state that we can understand, where we can actually calculate things about it and develop some sort of mechanistic understanding of how its different properties are related to each other, then I think that that would be a real achievement of this business, which even though we don't have a gravity dual of the Hubbard model. Okay, so now I'm going to try to do that. We'll see how far we've gotten. So to make progress on this, we need some more ingredients in our holographic models than we introduced yesterday. In particular, let's assume that our CFT has a conserved U1 current, so this is a restriction on which CFTs we're going to ask about. And as I mentioned, this means that there's a massless gauge field in the bulk. So this U1 current is going to be the electron charge current. And so a natural action for the gauge field in the bulk that nobody will argue with if I write it down is just a Maxwell term. This is a covariant Maxwell term. And so this is the analog of the analysis we did of this free scalar field in an empty de Sitter space. If we analyze the behavior of the Maxwell equation in a geometry which is asymptotically ADS, not necessarily ADS everywhere, but near the boundary it's ADS, then the behavior of solutions of this equation have a constant term, a term independent of z, and a term that falls off like z to some power depending on the dimension. And again, following the dictionary that we developed yesterday, we can interpret these two functions appearing in the asymptotic expansion of a solution of this equation as the source for the dual operator, which is the current. In particular, if I'm talking about the time component, the source for the time component of the current is the density, and the source for that is the chemical potential. The zero momentum source is the chemical potential, and the other component is the response, which for the time component is just the density. And so, following this Landau-Lifshitz formula that we talked about, the response is the momentum, the field momentum, with the z direction interpreted as the time, which if we evaluate this for the Maxwell action, you all know is the electric field in the z direction, which if I evaluate that on this solution gives me this density. So the electric field pointing in the radial direction in the limit as you approach the boundary is a measure of the density, of the charge density of the dual field theory. Okay, so that was one ingredient that we had to add. To look for a Fermi surface in the most simple-minded way, we're gonna want to try to compute this Fermion-Green's function that I was talking about, the thing you measure by photoemission experiments. And so we need to have a fermion operator whose two-point function we can calculate, and so that means that we should have some charged fermion. I want it to be charged because I want to think of this as electron charge, and I want it to be charged so I can think of this as a proxy for the bare electron operator. It's at short distances, it's not a very good proxy because this thing creates some lump of CFT excitations with some scaling behavior, and the electron operator creates an electron, but our purpose is to ask questions where that's not going to matter so much. And there are many examples of holographic constructions which realize these ingredients, and people have worked very hard to realize good ones. But the things I'm going to say aren't going to depend too much on those choices. At least I hope they won't. And so to compute this 2-point function, we have to solve the Dirac equation in the same way that to figure out the response of the gauge field, we have to solve the Maxwell equation. We have to solve the Dirac equation in the geometry, which is giving the saddle point of which is describing the equilibrium finite density state. Yeah, I guess I should have said I want to turn on a chemical potential for this U1 symmetry, and when I do that, with some assumptions, the ground state is a charged black hole in entity de Sitter space. So last time, I hope I convinced you that a neutral black hole in entity de Sitter space describes the saddle point of the thermal ensemble, so non-zero temperature ensemble of the dual CFT. And so you won't be too surprised if I tell you that a black hole which carries this charge, and therefore there's an electric field radiating towards the boundary, and therefore there's a non-zero density in the field theory, and the boundary value of the gauge field is some non-zero thing, describes the stationary point of the ensemble with finite chemical potential. This is a cartoon of this charged black hole. Here's the horizon. It's charged. I guess you can't tell that in the picture. And then we're going to scatter fermions off of it. Now there's an important little asterisk here, which we're going to have to come back to, which regards the question of whether this geometry can really describe the ground state of the system. So let's pause. What's the word? Hide that question for a little while. We'll come back to it. Now the fact that we're going to compute the 2-point functions of the fermions means that the only information we need to know about it is its quadratic action, its quadratic bulk action. And so that'll depend on 2 parameters. It'll depend on the charge of the fermion field under this gauge field and the mass of the fermion field. So the charge of the fermion encodes the charge of the operator, and the mass, in the same way as before, encodes the scaling dimension, the UV scaling dimension of the operator.
One question. In the boundary theory, the U1 symmetry is local or is global? So you have photons or?
It's a global symmetry of the boundary field theory.
So you don't have photons?
That's right. There's no photons in the boundary theory. And the reason, the motivation to do that is that they're usually screened. And in the metal, it's pretty safe, a safe assumption. So it's a gauge symmetry in the bulk. And part of the gauge symmetry in the bulk is actually not a redundancy of the Hilbert space in the bulk. The gauge transformations that don't fall off quite fast enough towards the boundary are actual symmetry transformations which realize the global symmetry of the boundary theory. Okay. All right. Other questions?
Are there also models with photons in the field theory?
Yes, actually. So there's a simple way to include to make the boundary gauge field dynamical. It's simple in principle, at least, which is here I'm imagining imposing Dirichlet boundary conditions on the gauge field. So I guess that's sort of implicit in this statement here that I'm fixing this constant as the source. And if you impose if you study the alternate quantization of the gauge field, this has the interpretation of imposing Neumann boundary conditions on the gauge field in the bulk, which means that its boundary value is a fluctuating thing. is a fluctuating gauge field on the boundary. So this is roughly allowing dynamical gauge fields. Yes, but I'm not going to do that.
I was going to say that.
Okay. So I think actually I don't understand what happens when you do this very well. I think other people may understand it better than I do. So please correct me. Did I say anything wrong about that? No. Okay. Yes.
So the 1/n expansion is the n is the number of flavors.
Oh, you're talking about in this field theory.
Yes.
Yes. Here it's the number of flavors. Yes.
But with the gravity duality,
It's a different n. Yeah.
Different.
Yeah. It's a different large n expansion. Yeah.
So there is something like color SU1 in the boundary.
In the examples we understand. Yes. But for as I tried to emphasize yesterday, the obvious roles that NC will play in our discussion is only to make the gravity theory classical. So its largeness is what makes the gravity theory classical, and it won't be clearly visible in any other way. Once we assume the existence of the gravity dual. Yeah. Though it's hard to hide though. Yes, please.
I think I got confused at some point that the gauge that you're considering in bulk,
Yes.
it corresponds to, for instance, this Kepler's boson that you.
No. Sorry, that was too many no's. The gauge field in the bulk is I'm introducing it merely so that the dual field theory has a conserved U1 symmetry, a global symmetry, which I want you to think of as fermion number. That's the symmetry
No
associated
particle
with.
creation.
Say again?
No particle creation.
Oh no! I don't mean like that. I mean, I just mean that there's a, the electron carries a charge, so the total number of electrons minus, let's say minus holes. I was going to say minus positrons. We could do that too. Is conserved, right? So even though you can pair create things, so there is particle creation in that sense, the total number is conserved. So it's and the point, I guess, that's sort of some metaphysical dressing of the discussion. But the real purpose is we want to conserve symmetry so we can add a chemical potential for it, so that we force the theory to be in a state with finite density, a finite density of the charge. Okay, and so you this question you asked though is an important one. We're going to find that there's some lambda quasiparticles that are killed by something, and so that something is the analog of the gauge field in the Fermi surface coupled to gauge field problem. It's the analog of the gaseous bosons, and
I disagree with that.
okay.
Because your quasi-particles don't carry gauge charges.
Okay, let's think about the pneumatic case.
Okay.
It's the analog of the thing that's killing the quasiparticles. That's all I mean.
This is an important point.
I agree. That's an important distinction. But okay, we'll see what it is. It's a lot more stuff. Is the answer. Okay, so solving this Dirac equation is something that I'm sure every one of you can do. And I know some of you have done. This is the answer in for some example. So this is as a function of frequency and momentum. This is a 3D plot of the imaginary part of the Green's function. I'm gonna skip the details of the Dirac equation. There's an appendix about it. And so you see this is zero frequency, and there's at some finite momentum this excitation passes through zero frequency. So there's a Fermi surface that's at this value that David Veg arduously evaluated to many digits. But it's not a Fermi liquid. And one way to see that it's not a Fermi liquid is you can measure the dispersion, and the dispersion relation is some power law with some exponent, which is certainly not 1. And that exponent varies when you vary these parameters labeling the theory. And also the residue vanishes. Notice when I say omega equals 0, I really mean the Fermi energy. 0. Okay, and so I just wrote some long numbers. Well, I guess these weren't that long. I wrote some detailed numerical numbers, which I told you depend on the parameters, and so I owe it to you to explain where those numbers come from. So these numbers characterize the arbitrarily low energy properties of the system, and so by the this lore that I motivated yesterday, that the end of the geometry farthest from the boundary is associated with the farthest infrared stuff, we might think that the thing we should do is to analyze the near horizon geometry of this black hole that we're studying. So near the horizon of the black hole, which is at some coordinate z0, the emblackening factor has not a linear zero, but a double zero. And so this is a property of zero temperature black holes. It's an extremely charged black hole, and you can see that if I can choose coordinates, coordinate zeta, which is z minus z0, this geometry is of the form ADS2, so just the same ADS that I've been writing, times a flat space that doesn't care about the radial coordinate. So okay, and by everything I said yesterday, this ADS2 has some conformal symmetries. The conformal symmetries of a 0 plus 1 dimensional conformal field theory, and this conformal symmetry is an emergent property of this ground state. So that, we started in a theory which was the CFT. So you may not be surprised that I'm talking about conformal symmetry, but we completely destroyed that symmetry by studying this theory in a state with finite chemical potential, which is a dimensionful quantity, which breaks the scaling. And so the fact that this geometry in the infrared has this new scale invariance it's an output of the duality, to the extent that you believe this is the ground state. And notice that this geometry has a scale invariance with a dynamical exponent which is infinity, in the following sense. So I said, did I introduce the dynamical exponent? Maybe I didn't. So previously we thought just about relativistic theories where we scale t in the same way as x. Somebody mentioned that there are examples where we can scale the spatial directions differently, and the power with which we scale space is 1 over z, where z is called the dynamical exponent. And you see in this case the scale invariance acts on xi and acts on the time coordinate, but it doesn't act at all on the space coordinate. So this has z equals infinity. Okay, and so this Reisner-Nordstrom charged ADS black hole geometry, this black hole geometry that I'm talking about, the zero temperature charged black hole, is a picture of the RG flow from this relativistic CFT in d plus 1 dimensions, in d dimensions, which is dual to the ADS theory near the boundary, deformed by this relevant operator, which is the chemical potential, flowing to this non-relativistic conformal fixed point, which is the dual of this geometry. And so we can use this geometry and the holographic prescription to compute the low energy properties. Even if we don't know microscopically a description of this theory, the ADS-CFT dictionary tells us how to compute its properties. Okay, and in particular, this idea leads to a calculational prescription for solving the Dirac equation at low frequencies, which previously had been very successful in the calculations that initially led to ADS-CFT, where people were studying the geometries created by back reaction of d-branes in flat space, where there was the analog of this was flat space, and the analog of this was the ADS geometry, which is dual to the CFT. So that was a historical comment, which you should ignore if you want. Okay, and this calculation, it's a 19th century calculation, leads to the following complicated looking formula. It's a little intimidating, so it's color coded. You can't really see the colors, can you? Can you see the colors? That's because this is infrared and this is ultraviolet. Yeah. Okay. So yeah, that's a little annoying. So these coefficients with lots of labels on them, these b's and these a's, are real numbers, and they're colored ultraviolet because they're associated with the behavior of the Dirac equation far from the horizon, such as the zero frequency Dirac equation in the full black hole geometry, and those are real. And this incredibly fancy g here is the 2-point function of the fermion operator in this infrared fixed point theory, so in this ADS2 theory. And so it's the correlation function of a scaling operator in a 0 plus 1 dimensional CFT. That means that in frequency space it's a power law in frequency. That's what it means for it to be a CFT. I guess it's the fact that it's a CFT also constrains this. That's what it means for it to be scale invariant in 1 dimension. So this nu here is the dimension, the 0 plus 1 dimensional dimension of some fermionic operator. And so this is the Green's function of the big theory, of the electron-like operator in the big theory, and it's constructed from this Green's function in this infrared fixed point, and then these UV coefficients. Okay, and so if you think about this as a function of frequency and momentum, so these A's and B's depend on momentum, but don't depend on frequency. You can see that if you ask where does this have poles at 0 frequency, you could see the following thing, which I'll illustrate a little more in a second. The location of the Fermi surface is determined by, in fact, you want to ask where this coefficient vanishes. It's determined by the short distance structure. It depends on these UV coefficients. You have to know what this A is, and so that's in this the same situation as in a solid, where the location of the Fermi surface depends on the band structure, depends on the organization of the ions. On the other hand, the behavior near the Fermi surface, once you know that there's some zero of this function of k, the behavior near the Fermi surface, the scaling in frequency, is determined by this infrared CFT exponent. It's this universal thing, and this exponent nu is computable in terms of the data we have, in terms of the mass and the charge and the momentum at which the Fermi surface occurs, where this L2 is the ADS radius of the infrared ADS2. Okay, so in a little more detail, let's think about what this means for a Fermi surface. So suppose you have a value of this coefficient, A plus, which vanishes. Look at the behavior of the Green's function near there. So here I've just renamed some things. So k perp is just the deviation from that special momentum where that coefficient vanishes. I divided by some VF to make it look like this Fermi liquid formula I wrote before. And then this thing here plays the role of the self-energy. I guess you could say this whole thing is this is the correction to the self-energy, which is this curly G. These other coefficients are all real UV data. And there's an important dichotomy here between the case where this exponent nu is less than a half and when it's bigger than a half. When it's bigger than a half, that means that at low frequencies, omega to some power bigger than a half is small compared to omega, when omega is small. And so we can ignore this, and the dispersion is just determined by this linear bit. And so the dispersion is linear, and the imaginary part comes all from this Green's function, which I should have said is a complex function. And so the motion of the pole in the complex frequency plane as I vary the momentum through the Fermi momentum is something like this. It starts far from the real axis in the lower half plane. This is an unstable, describing an unstable particle, a resonance. And as you move towards kf, it moves, it sort of slowly approaches omega equals 0, and then heads back into the complex plane. And this is this describes a stable particle. The exponent with which this approaches 0 is something other than 2. It's some power that depends on this nu. And this is in contrast with what happens when nu is smaller than a half, where this term dominates the dispersion. It dominates the behavior of the real part and the imaginary part. And because the same exponent leads to both the real part and the imaginary part, the motion of the pole in the complex plane is a straight line. And so therefore, the width, which is determined by this distance, is of the order of the frequency, is parametrically the same order as the frequency. And it's not a stable quasi-particle, and as a function of k perp, it's some power law which we can now compute in terms of this infrared exponent. So not a stable quasi-particle in this case. Okay, And so let's talk a little bit about what's happening to the quasi-particles from the point of view of this holographic calculation. Right at the Fermi surface, so if you just forget about this thing, which vanishes at omega equals 0 after all, the problem that we're solving to find the Fermi surface is the problem of finding a bound state of this Dirac equation in this black hole. And we can rewrite that as a Schrodinger problem, so where the profile of the fermion field plays the role of the wave function, and the analog of the time coordinate is some coordinate which is a function of the radial coordinate, which is made from the radial coordinate, which I've plotted here. So this is the UV end of the geometry, and this is the horizon of the black hole, and this is the effective Schrodinger potential for various values of the frequency.
How do you get this potential?
So this rewrite the Dirac equation in this way. This S is one hint is that this S is the tortoise coordinate.
There has to be some spin aspect as well.
This is one component of the Dirac equation, and you can solve for the other in terms of it to make a single second order equation. Yeah. I'm sorry, I'm giving you a hard time just because I'm trying to be brief, but I'm happy to explain. Right. Yeah, that's the idea. So roughly plug one component of the Dirac equation into the other one. Yeah. So there's some ambiguity in here, I should emphasize. So for the scalar wave equation, there's a unique and best way to rewrite it as a Schrodinger equation, where the role of the energy in the Schrodinger problem is played by the momentum squared. For the Dirac equation, I'm not sure if this is true, but I have never found a way to rewrite it as a Schrodinger problem where the momentum plays the role of the energy. Rather, I've rewritten it as a zero energy Schrodinger problem, where the momentum appears as a parameter in the potential. Yeah. So there's actually quite a bit of ambiguity in doing that. You can choose different independent variables, which will give the same answer. So this is some choice. Actually, this picture is probably for the scalar problem.
But still, the linear term in K is always present. That is important.
Linear term in K is always present. Linear term in K is always present.
First derivative is true.
Sorry, I didn't understand.
I mean, this is spin structure. When you cannot just
It certainly is possible to rewrite the Dirac equation as a Schrodinger equation. Whether you like the way I've done it is a different question. Yeah. Okay. So, but this is instructive for the sole reason that we know about one-dimensional Schrodinger problems, right? Because
your statement is only true for 1D. The K perp is a parameter inside D, right?
Oh yes, it is certainly important that I'm using rotation invariance. So this momentum is just in one. I'm aligning my axes with the momentum. Yeah, thank you. Yeah. Okay, I didn't understand what you were asking. Right. So it's a 1D problem. Right. Good. And so let's see. So right at the Fermi surface, the effective potential looks like this. So it's this one. And so that potential you can all see with your eyeballs that has a bound state, right, which is this red thing that's drawn there. On the other hand, away from the Fermi surface, the potential plunges to some fiery death near the horizon of the black hole. It reaches energy is much lower than the energy which the bound state occurs, and so it's possible for the bound state to tunnel into this. So this is this ADS2 region of the black hole. It's possible for it to tunnel into this ADS2 region, and a simple calculation of the tunneling rate, which is justified by taking low frequency. The WKB approximation is good because of small frequency. Shows that, let's see, how does it go? This distance through the potential is log omega. Did I get this right? Yes. And this height is related to nu. It's the height is nu squared, and so you have to take the square root, and so this is e to the 2 nu log omega is the tunneling rate, which is omega to the 2 nu, which is the lifetime that we found. Yes, please. Right. It's meant to be a profile of the bound state wave function right at the Fermi surface. Yes, good.
So this wave function has almost no support in ADS2.
That's right. That's right. Yeah, it has an exponential tail. That's
So
right.
that distinguishes it from the states that make up the cut, which would have significant support in ADS2.
Yes, that's right. That's right. Because this is the statement that there's mixing between this state and states which are supported there.
Yeah, if you went a slightly non-zero temperature, then the cut would break up into a series of poles.
That's correct. Yes.
And each of these poles would represent states with a lot of support in ADS2, right?
Yes, that's correct. Yes. Yeah. Yes, and it makes beautiful pictures, which I don't think I have any on my slides. Okay, so the conclusion of this is the following photo emission pictures in the three cases. So this is so in this case, when nu is bigger than a half, the fact that this bound state is interacting with this infrared CFT is not enough to kill it. It's still stable, and so it has this linear dispersion. It's a narrow resonance. If nu is less than a half, the quasi-particle decays by interacting with this infrared CFT. We'll understand a little more in a moment how it interacts, but this leads to this power law dispersion and some huge particle-hole asymmetry. And then there's this interesting case in the middle, which is worth mentioning, because the Green's function in this case is exactly of the form that people wrote down roughly with some motivation as a fit to the photo emission spectra in this region of the high temperature superconductor phase diagram. And in this case, so it's called a marginal Fermi liquid because the quasi-particles are marginally stable. If the imaginary part were any bigger, it would be unstable. Okay, and the lifetime goes to 0 logarithmically with the frequency. The residue goes to 0 logarithmically. Okay, and so I guess I have to mention the transport properties, and since I said that this linear T resistivity is sort of the most prominent mystery, and I have to say right away that the contribution to the conductivity from this Fermi surface that we've just discussed is not the dominant contribution to the conductivity in the system if you hooked up leads to it, because there's a density of charge which is present even classically in the system. Described by this computation with let me just point at it by this computation here that we did, and if you apply an electric field to this, it will well, okay, if you don't somehow break translation invariance, it'll just accelerate. But even if you somehow get around that, it gives a contribution which is of order n squared, something leading order in the holographic expansion. The contribution, we can nevertheless isolate the contribution to the conductivity from this Fermi surface that we found, which comes from a Witten diagram like this. So again, this is meant to indicate the boundary of ADS. I drew it as a straight line because we're studying a case where the field here is living on a plane. And this wiggly line is the propagation of the gauge field. This is the insertion of the current to compute the current 2-point function in the Kubo formula. There's a 1 over omega. And this is the spinor field in the bulk. And DC conductivity is proportional to the imaginary part, and so that's why I've drawn this little line cutting the diagram. Okay, and a calculation whose details are apparently going to appear sometime, even though we began working on this in June of 2009, shows that the conductivity in this case is given by the power law that you'd expect from the single particle lifetime. And the way to understand why this is the case is that, unlike in this problem where the quasi-particles are scattering off of a massless gauge field whose excitations are supported at 0 momentum, here they're scattering off of this infrared CFT with dynamical exponent infinity. The fact that the dynamical exponent is infinity means roughly that, so here's linear dispersion. This is omega, this is k. Here's quadratic dispersion. This is k, this is z equals 1, z equals 2. Okay, here's z equals 4. And so as you can see, if we keep going here, eventually we'll get to a situation where the dispersion is like this, there's gapless excitations at basically every momentum. And so there's no reason that the scatterings which kill the quasi-particles preserve their momenta. There's large angle scattering. And so the same process which kills the quasi-particles is efficient at dissipating the current. And so we get this exponent. Okay. And in particular, in the case where we have this marginal Fermi liquid behavior, we get this linear T. Okay, so now I have to talk about this asterisk, about the question of whether this charged black hole could ever describe the true ground state of anything. Are there any questions before we, while we're still celebrating the happiness of this linear T residue? Yes?
What do you exactly mean by contribution to the conductivity from the Fermi surface?
Well, so yeah, so I mean, the conductivity is determined from this 2-point function, and in an expansion in powers of n squared, we can expand this 2-point function, and that gets lots of contributions. In particular, at leading order n squared, it's a simple classical calculation. The answer is infinity. We can regulate that and ignore it. And then at one loop, anything that couples to the gauge field can run in a loop like this and make some contribution. And also, for example, renormalization of the coupling constant can make some contribution at one loop also. And so it is actually a little bit dicey to say what I mean. It's not just the n counting. It's also, I'm interested in the behavior which is singular in temperature at low temperature. And so and this is the only contribution that has that property.
Another question. So it seems that you get non-Fermi liquid behavior because you, in your gravity calculation, introduce some z, right? The gravity background. So what is the gravity interpretation of this? Because what you did, you solved the Dirac equation in a different background, which depend on some z, right?
Okay, I did that, yes.
Yeah. So what's the interpretation of this z in the gravity?
Interpretation of z.
Yeah. Because this
Sorry, by
seems
z,
to be,
by
seems
z
to be
you
that
mean
this
that,
is the key point, right?
by z do you mean the dynamical exponent?
Yeah.
Well, actually, I disagree a little bit. The infrared geometry could have been something with it could have been relativistic, and we could still have found something similar to this. But okay, but you're right that for many of the features that I've described, in particular the fact that the self-energy of the fermions is momentum independent, is a consequence of the fact that the infrared CFT has z equals infinity. And well, the interpretation of this is so this is the interpretation, right? It means that roughly that at arbitrary momentum, not too big that we get outside the regime where we can think about the infrared CFT, there are low energy excitation. That means that roughly each little patch of space in this infrared CFT is independently a critical system. And so there's a huge literature on what's called dynamical mean field theory, where this is sort of the starting point of a treatment of for example, the Hubbard model, where when one assumes that the self-energy of each that the self-energy is momentum independent, and so this is sort of this, and it's called local quantum criticality. Local in the sense that each patch is independently critical.
Yeah, but my
And so
question
that's the interpretation.
it's not about the field theory, but it's more about the gravity tool. So why you introduce this background with this z? It's because you have this choice.
I introduced this background with this z because it's the solution of the equations of motion with the right boundary conditions.
Oh, okay.
Yeah. So this, I guess I should have emphasized this more.
Okay.
So when I said that, when I first introduced this charged black hole, I did it because we were studying Einstein-Maxwell theory in de Sitter space, and
This is what you get.
if I demand that the boundary condition, if that's the only thing in the world, and I demand that the gauge field
Okay.
approaches a constant in the UV boundary, then the solution is this. Yeah.
John, can you make a comment on mechanisms that could give you u equals a half robust?
I can comment that I don't know how to do it. Yeah. So right. So this is an important question. So this this nu equals a half is the value of this exponent which happens to match the behavior in these systems. And from the point of view of this calculation, there's no reason that this one is the best. It's there's some set of values of the mass and the charge for which this is realized, and I don't know why it's special from a microscopic quantum gravity point of view.
Has anyone tried model building? Ways to just drive you to this value?
Yeah. David Vegg had a good idea about how to do this. I don't know if he's here today.
Seriously, why would you want? This is not the real prediction of this model. There's a delta function at 0 frequency.
You mean in the conductivity?
Yes.
Okay.
No,
I'm sorry to be
that,
critical.
that could be spread out by
But that will
other
completely
influences,
change
but that's
the
just going to
distribution.
dominate this.
Yes.
Because of the n squared.
That's the elephant in the room. We can't ignore it.
So what Sabir's saying is
spread out without preserving some of the linear.
Well, that's the hard problem.
yeah. So what Sabir's saying is an important thing to emphasize, which
That's the problem that we've been worrying about for 20 years. Getting an additive contribution because of some lots of boson giving you an addition, that's been understood for 20 years. We know how to do that. That's not the easy part.
Okay. I agree. I agree that the reason that we did this calculation, the answer is completely obvious. I agree with you. It's just, if you like, it's a check on the machinery. Yeah.
Fine. Yes, of course.
Yes. Which is actually quite hard to do. Okay, so there are two shortcomings to this calculation. One of which Sabir is emphasizing, which is really the more important one, which is that this Fermi surface. I mean, it's in this picture here. This Fermi surface, which we're interested in here, is a small part of a much larger system. And in particular, if we compute the density of these fermions, the density of the fermions whose two-point function we're computing in this ground state, the answer comes from a one-loop calculation. It comes from this diagram. This is the boundary of ADS. This is the fermions. This is of order n to the 0 because it's down by a factor of n squared relative to the classical calculation, which was on the slide that I just showed you. And so this is much less than the tree level density, which is proportional to n squared. And so these excitations that we're studying here are a small part of a much larger system, and that much larger system is the reason that this is happening. I'm going to come back to that in a moment. That's the motivation for this work that I was referring to as about electron stars. There's a second issue, which is not entirely independent, but somewhat independent, which is that not only is this state, describing not quite the Fermi surface we want, it also kind of doesn't exist. So what I mean by that is, you may have noticed that the Bekenstein-Hawking formula tells us that the entropy of a black hole is proportional to its area, at least in Einstein gravity, which is what we're studying, and the area of the horizon of this charged black hole is non-zero. Right? It's roughly the area of the ADS2, the spatial directions of the ADS2. But on the other hand, I've told you that it describes a zero temperature black hole. Right? The two zeros, the zeros of the Blackney factor coalesce. It describes a t equals 0 state. And so that means that we're describing a state which has non-zero entropy at zero temperature, which violates the third law of thermodynamics. The reason that there's a third law of thermodynamics is that a system which a state of a system which you might think was a ground state which had this property, well, means it has some huge degeneracy of its Hamiltonian, and such a system will, if you perturb it even a little bit, will find some way to lift that degeneracy. And so this leads us to expect that the state should be unstable at low temperatures. And we can ask, to what is it unstable? And one answer which is kind of a happy answer is the following phenomenon, which is worth mentioning in its own right, which is that in many examples that realize the collection of ingredients for our holographic system that I was asking for, there are also some charged scalar fields. And in this case, if we study the system at low temperature, these things can condense. So charged bosons with a finite chemical potential, it's not too surprising that they condense and then they break the C1 symmetry. And one way to see this is so in the spinor calculation, this Green's function that we computed it's possible to show it has poles only in the lower half frequency plane. That means that they're all unstable particles, but if we populate these excitations, those excitations decay in time. On the other hand, if we do the same calculation for a scalar field, a boson field, we find poles in the upper half plane. That's the bad one, because that means that the time evolution of the response grows in time. And so this describes an instability, and the reason that this happens is the following. So a charged black hole spontaneously emits charged particles. When the black hole is in ADS, those particles can't escape to some asymptotic infinity, so they end up attacking the black hole again. In the case of fermionic fields, the thing that happens is just we fill available negative energy states until they're filled, and that's the end of the story. But in the boson case, we can keep filling them, and so they cause this kind of stimulated emission, or in the black hole literature, it's called superradiance. And so a holographic superconductor is literally a black hole laser, in this sense. Which, it's worth mentioning that depending on the charge and mass of the boson field, they sometimes don't condense. If the mass is too big or the charge is too small, this is the dimension of the boson operator. This is its charge. It's in this window. It exhibits the holographic superconducting instability. And so if you wanted to construct a holographic state where this holographic superconductor instability did not set in, you'd have to engineer a ground state of string theory where all of the charged bosons were in this window. This problem is very much like the problem of moduli stabilization in trying to construct string vacua, which might look like our world. Okay, but it's difficult not to notice that many of the systems about which we're telling the story also have a superconducting region in their phase diagram, right? It's sitting there in front of your faces. And so maybe it's not such a terrible thing that there can be this superconducting instability. Okay, that's been my perspective. And okay, I'm going to skip this. We can study the should I skip it? Yeah. We can study the fermion response in the superconducting state. There's some interesting things to say about it, which I won't say. Okay, and so
were your general remarks on the third law of thermodynamics, can I regard that as a prediction that no zero temperature black hole in string theory should have finite entropy?
Yeah, I think it's not my prediction. It's like Nernst's prediction.
Do you agree with this prediction?
Well, okay. So the issue is confused by the large n limit. So this it may be that at infinite n, that things can be stable, and the degeneracy is only resolved at order e to the minus n squared.
What about supersymmetric black holes? I mean, we know of supersymmetric black holes in ADS that are linearly stable, right? I mean, they're protected by supersymmetry.
Yes, yes. That's because supersymmetry is opposed to physics. These things are. Still, it's not. Yeah. Third law of thermodynamics.
Question. I mean.
Yeah, but the third law of thermodynamics is a consequence of physics, right?
Oh, sure.
Yeah.
I'm just giving an answer to Shiraz. There are black holes which are stable even at t equals 0.
No, but they're linearly stable under gravity perturbation. I mean, there could be other modes which destabilize them. I don't think it settles the question completely.
Are they stable against modes that break supersymmetry?
Yes.
Against all modes?
Yeah.
Yes. You can show that supersymmetric black holes are stable against linear perturbation.
Yeah, this is true. No, certainly if you have some reason that protects the degeneracy, then there can be a degeneracy.
No, but if your perturbations break break all perturbations.
You considering
all
perturbations that break
including
all of
everything.
supersymmetry?
Huh?
Then
Including
I
supersymmetry.
don't know. Then I don't know.
That's the crucial question.
Oh, I see.
You could certainly get a fixed point which has some beautiful enlarged symmetry, but it has to be stable to all linear perturbations in all directions.
Yes, I think he's right though that there are examples which non-supersymmetric linear fluctuations are stable around supersymmetry.
But I think it's also important to comment that none of these examples have planar horizons in empty space.
That is true. That is absolutely true.
Yeah, so these things cannot be BPS.
Well, if you don't have planar horizon, then you're not in the thermodynamic limit. There is no third law.
Well, they could be in the thermodynamic limit because of some large charge.
If they're large
It
enough,
could be like a
of
big
course.
molecule.
But it's sitting on a sphere. Right?
Yes,
Well,
yes.
then there's no Nernst law for that.
I think there still is. But, you know, if like a big enough molecule.
No. Third law of thermodynamics applies only in thermodynamic limit.
The thermodynamic limit applies pretty well to, you know, protein.
Okay, fine.
Yeah, no, this is a good point. Okay, so but I'm let's see. Okay, so yeah, so this picture is actually my answer to Shiraz's question. This is what I said. The third law of thermodynamics is violated, and this is, I guess it's important to emphasize, this is a manifestation of the black hole information problem, in the sense that in the calculation that I've been describing, we took the n goes to infinity limit before doing anything. Right? We started our discussion using classical gravity, and that limit doesn't commute with taking a long time limit, which is what you need to do to let the system find its true ground state. And so I think a useful cartoon of the phase diagram of the system as a function of temperature and as a function of 1 over n is the following. So up here, the thing is a relativistic CFT. It's something that we don't care about for doing condensed matter physics, and we want to ignore this part of the phase diagram. That's his dragons. If there's a superconducting instability, so here's the chemical potential. If there's a superconducting instability that that happens in somewhere here, maybe it's not parametrically lower than the chemical potential, but there's some window. Otherwise, it's not so interesting. And this is the regime where this the physics of this Fermi surface is relevant. And it's possible that if we do engineer some string vacuum where these things are all absent, the holographic superconducting critical temperatures are all 0, then it may be that the only instabilities are, for example, quantum gravity tunneling, for example, which would happen with amplitudes of order e to the minus 1 over g Newton, which is e to the minus n squared. And so that would give a independence of the critical temperature, which looks something like this, which is T star, the temperature below which one sees different physics is of order e to the minus n squared. So here you would see something else, whatever the true ground state is, and in this window you would see the physics we've been talking about.
There's no 1 over n splitting of the degeneracy of the black hole.
No. And there's a simple way to see that, which is just 1 over n corrections don't change the solution, right? They you have to completely get rid of the horizon from a perturbative correction.
Can't do that with G-string correction.
No, you can't do it with perturbative corrections, right? Because it requires a rearrangement of order n squared degrees of freedom at each point in the space-time. Yeah, so that's the reason that it's such a small effect. One slightly less fancy-sounding mechanism for lifting the degeneracy than just saying quantum gravity effects was pointed out by these people, including David, which is that this phenomenon of pair production of particles near the charged black hole horizon that I mentioned means that you create fermions near the horizon, since that's what it said, and these charged fermions in the bulk screen the electric field. The electric field is playing the role of holding up this ADS2 geometry, and including the back reaction of these particles leads to a ground state, if we imagine trying to study finite n, which is a Lifshitz geometry, with large but not infinite z. So this ADS2 geometry was this, right? The spatial directions don't care about the radial direction. If a geometry where so this z is different than that z. This z is a coordinate. This math frac z is the dynamical exponent. And so you see if this geometry, which was I guess first written down by Kachru, Xiaolu, and Mulligan, is the answer to a question somebody asked about whether we can study scale invariant theories with other dynamical exponents. So because you see this thing has a scale invariance where I scale x with lambda to the 1 over z and t with lambda to the 1. Okay, and so as I take the limit where this curly z goes to infinity, I recover the ADS2 geometry. Okay. Okay, how am I doing on time? All right, okay, I guess I should mention this. So you may have been a little bewildered by this fancy formula I displayed from the matching calculation, which related the UV CFT Green's function, the UV Green's function to the infrared CFT Green's function. A very simple way to understand the structure of that equation is by thinking about the following so-called semi-holographic description of this state, which is where we imagine representing the bound state excitation by a free fermion, something with a linear dispersion, and coupling it to an operator here called chi, which we imagine to be the operator in the infrared CFT, coupling it by this kind of hybridization, just this quadratic mixing. So what I mean by saying chi is the infrared CFT operator is that its Green's function, that is the thing you get if you invert this, is exactly this infrared CFT Green's function that I've been talking about. And so computing this two-point function in this theory is you can do by just summing a geometric series, and it gives exactly this form that we were discussing. And you can see that doing scaling in this theory, when this exponent nu is less than a half, this coupling, this coefficient which I didn't name here, is a relevant perturbation. Okay, so this is a useful cartoon of the calculation. Okay, but I want to, in the remaining few minutes, I want to talk about progress towards overcoming this problem, which Sabir was emphasizing, rightly so, that the Fermi surface that we're studying is just a small part of a much bigger system, and so we're actually using very little of the holographic machinery in studying it. Okay, so the first progress in this direction was taking seriously this picture of thinking about letting the fermions back react on the geometry. Here, even if we're trying our best to ignore their back reaction, they affect the far infrared geometry. In this work, which was mostly done by Sean, and I'm sure he'll talk about it more later in the week, they chose the charge and the mass of the fermion so that they could study the bulk fermions in a regime where they could think about them as a fluid, and therefore, in a very simple way, include their gravitational back reaction. And so they constructed these nice solutions called electron star geometries. And one property of these solutions that I think is worth emphasizing is that this limit of parameters involves large charge and large mass. And as you might expect, being in a fluid approximation means that we have to, we're treating these fermions as point particles. It means we have to be in a regime where the quantum numbers are very large. And so you won't be too surprised when I say that when I compute the Green's functions in this state, I find instead of one Fermi surface, I find many, many, many Fermi surfaces, a number of order the control parameter. And so the next step towards improving the situation was made by Sabir, which was a holographic model, which is a Fermi liquid. And the starting point is just to cut off the ADS geometry at some radial coordinate. So this is like a toy model of confinement, of introducing a mass gap, and solve for the wave functions of the fermions in the Hartree approximation. That is, we imagine guessing some potential, some electrostatic potential, solving the Dirac equation in that background. Yes.
Why this is a model of a Fermi liquid if you cut off?
That's the answer. The answer is
this is the answer, but
yes.
Why?
So that's what I'm trying to explain.
Okay, so you're going to explain this now.
But the important, the reason I'm talking about it though is because it's a step towards improving this situation. So it's a step moving away from this fluid limit where the number of fermion particles can be order 1. Okay, and so turn on a chemical potential. Okay, this is the spectrum of the direct equation in this box without a chemical potential. Turn on a chemical potential. Everybody see that? Yeah. And then solve for fill the levels that need to be filled, solve for the resulting density, and then do it again. Compute the spectrum again in that background and do it until it converges. And the outcome is that it is a Fermi liquid in the sense that there are stable quasiparticles. At leading order in N, they're exactly stable. Okay. And okay, so I got excited about trying to elaborate on the situation from the following point of view. A confining geometry here describes is a summary in pictures of the complicated result of dynamics of the dual gauge fields, right? It says that those gauge fields confine, and the end result is that there's a mass gap. Adding fermions here means that we're introducing low energy excitations that carry, adding a chemical potential at least, it means we're adding low energy excitations that at least some of which must carry that color charge. And the effect of doing that is inevitably that gauge field, which in the vacuum without the chemical potential was confining, will be screened, and its effects will be lessened. And so you might think that by cranking up the chemical potential and including the gravitational back reaction, which is the dual of including the dynamics of those charged fields, we might be able to make this geometry deconfine. We made a little progress towards doing that in this model, but we had to retrench a little bit. And the basic question that I had to ask is, where does it go after? What can the state be after it deconfines? What can the state of the fermions be? And so to answer that question, we thought about a very simply stated problem, which is just still in this probe limit, where we don't include the back reaction on the gravity. So the field theory interpretation of which is we're studying a CFT where most of the degrees of freedom are neutral, are not charged into this gauge field. Let's see if we can take away this cutoff. So solve the same problem, but think of this cutoff on the geometry as just a regulator, as an infrared regulator, and solve again this problem of find the spectrum of the Dirac equation self-consistently in the presence of some potential, self-consistently with Gauss's law with the density produced by those fermions, by filling the Fermi sea with those fermions. Okay, so this is these two equations in a little bit more detail, which I'm going to skip because I have 0 minutes left. But the result that we found, which I'm quite excited about, is that it's actually possible to take this limit where the cutoff, so this is a sequence of values of this cutoff, goes to infinity, which in our numerics so far means 50. I guess we did a few larger values. And there's a state of these fermions where they hold themselves up. So this is the density of fermions as a function of z. They hold themselves up from collapsing into this gravitational well because of Pauli repulsion and electrostatic repulsion. And the spectrum looks something like this. If we compute the photoemission spectrum, it looks like this. So this is the light cone of the CFT. You can see that there are all of these CFT excitations inside that light cone. This is a single Fermi surface here, and you can see from this picture that this is a stable excitation. It's very narrow, and there's a kinematical reason for this, which is that the way in which the Fermi surface excitation could decay is by interacting with this infrared CFT stuff, right? That's the mechanism I've been talking about. And in this problem, unlike in the previous one, the infrared CFT stuff is relativistic with a light cone that's centered at the same origin as in the UV theory. Whereas the Fermi surface excitations are sitting somewhere here, as this is frequency, this is momentum, this is frequency. So the Fermi surface is here, 0 frequency, finite momentum. And so kinematically, at leading order, there's no way for them to interact. And so this is a situation which I think may be improved by by including the back reaction.
John, do I
Yes.
understand that you're saying that z is equal to 1 is the case there?
Yeah, z equals 1.
Why did you come up 1 and not say 3 or something?
You mean for the Fermi
Anything
surface?
finite would have given you a similar result.
The Fermi surface z, do you mean?
No, the light cone. Or is that just...
Oh, sorry, the reason is because we're in this probe approximation. So the geometry is just fixed to be ADS from the
right,
beginning.
So if you back reacted, you
Yes.
would get z is equal
Yes.
to 5.7 or something.
yes, that's right. Yeah, so this, okay.
I mean, you know, you obey Latin-based theorem. Right?
Yes, for the same reason that you do. Yes. Yeah, there's nothing frightening about that. So then, as Julian is
It
emphasizing,
means function out of non-Fermi liquid.
no, it's Fermi liquid. Yeah, just like yours. Yeah. So far, because of this kinematical fact that I just described, because of the fact that we're using this probe limit and assuming that the geometry is just ADS, we find perfectly stable Landau quasiparticles, not even Landau, Fermi gas quasiparticles. This can be different when we include the gravitational back reaction, which we're working on, or I guess Andrea is working on while I'm here talking to you. And in that case, we don't know what happens. I'm very excited to find out. Okay. I think I'm going to skip this comment. I'm going to skip these slides, and maybe we conclude. Yeah. Okay. So this is my last slide. I just want to emphasize a little bit that holographic duality is a powerful tool. We need to use it wisely, and hopefully some of the things I've said have helped to suggest how best to use it. So in particular, it clearly gives us wonderful toy models of strongly interacting systems, and about those toy models we can learn everything we might ever want to know, really. But of course, as always in physics, toy models are only useful if you do the right things with them, right? You don't abuse the toy models. And so one example of a thing that you should not be doing with it is trying to compute critical exponents, right? The critical exponents you've seen depend on these landscape parameters, right? The mass and the charge of the fermionic operator determine the nu near the Fermi surface. So that's not something that you should be trying to predict, because in order to say something about a prediction of that, you need to understand the string landscape, which, well, okay, go ahead. Yeah, we don't understand it. Another lesson, which I think is also important, is thermodynamics doesn't do that great a job between telling the difference between strongly coupled theories and weakly coupled theories. So in the n=4 superring Mills, the free energy differs at weak and strong coupling by a factor of 3/4. A similar statement is true in lattice QCD between low and high temperature. On the other hand, transport properties are very different between weak and strong coupling. So something I didn't really talk about was this eta over S, which a weak coupling is infinity, and a strong coupling is some nice order 1 number. Far from equilibrium physics is something where I think we don't even really know what the right questions to ask are. At least I don't. But holography is clearly a wonderful tool for trying to think about them. And then I guess finally, I think David's question yesterday is really a very good one. Of it seems kind of shocking that we haven't, using holography, come across some sort of qualitatively new physical phenomena. And maybe we have, and we just thought it was too crazy because we haven't seen it in experiments. But it's I think, given the simplicity of you draw some picture and it tells you about some phase of matter, it seems like a real opportunity that to find something something really new. So yeah, okay, that's the end.
Questions?
So in describing confinement, I thought you used the words confinement and mass gap interchangeably. Are they actually the same thing?
Yeah, so those are not the same thing. You're okay. Yeah, this is a complicated story. I guess the thing I was interested in is the confinement. If there are a few light modes that survive the confinement, I'm okay with that. So sometimes there's like Goldstone modes from chiral symmetry breaking or something like this. Pions. Yeah, but that for my purposes, I could use them interchangeably.
Okay, I think we should probably break for coffee and get caffeinated up for the next talk. Not that the next talk will need caffeine. Fantastic. But John will be around until mid-afternoon, I think, if you want to ask any more questions. But let's thank John for some excellent.